Did you remove the name? Sì. Yes. Can youそう言われると僕は本気で。いや、それは分かるの。いや、朝そう言ってたからかなと思って。英語は私は日本じゃんでしょ。あ、いやいや、僕も英語喋れる。あ、そう。あいつじゃないよ。Okay, so let's start the afternoon session of the day. Okay. So it's my great pleasure to introduce the speaker, Professor Antonio Segatti from University of Pavia. The title of his talk is on some results on the heat flow for half harmonic maps. Please start.
Okay, so thank you very much, Laura, and thanks to the organizers. It's an immense honor to participate to this workshop. I love Japan and I love Spain, so it's a perfect combination for me to be here this week. So it's and it's also I'm very happy to tell you something about this work that it's done in collaboration with Ali Haider, Yannick Sira, and Gianni Wang. So let me start from the very beginning of the story, and I mean from the first slide will be a bit dense. But then I will explain, I try to focus on examples. So we start with, say, two manifolds, say M and N. Essentially, in the rest of the talk, M will be, for most of the times, the whole space, the whole Euclidean space or some domain. And N, on the contrary, will be a manifold, say, usually a compact manifold. Okay, so we want to study this energy. So it's the Dirichlet energy. Here, nabla is really the gradient because we are thinking to maps that go from your your domain M to some Rk, and you impose the constraint on the map that takes values in this manifold N. Okay, so this energy is perfectly defined in this class, so you can define, I mean, with quite work, this energy class. So it's consists of maps with H1 regularity, with takes values in Rk, and you have that the constraint. So this is, I mean, classical. And so what you want to do with this energy? Well, you want to study critical points and discover that, say, a critical point of this energy, you can compute its Euler-Lagrange equation. And its Euler-Lagrange equation, due to the fact that you are imposing this constraint, well, its Euler-Lagrange equation is a nonlinear PD that has this form. So you take minus Laplacian and you impose that the vector minus Laplacian is perpendicular to the tangent space at the point u of x of the manifold N. Okay, so I will call harmonic map, say, a map that is a solution of this nonlinear PD. Of course, if N is really Rk, then here you are just solving minus Laplacian of u equal to 0. And the nonlinearity exactly comes from the fact that you are, say, it's always, say, if N is it's not a whole space, this equation is always nonlinear, of course. And the fact that M is a manifold or M is a domain in Rd, I mean, it's just a matter of computing this Laplace Beltrami operator or the usual Laplacian. So it's for the moment, it's not a big issue. Okay, these maps have been studied quite a lot in the last 60 years, say, and this is just a very short list of some names that studied this kind of problems. Okay, so this is the context. Let me switch to a very particular situation, particular but difficult situation. The case in which you take M to be a domain in some Rm, so a flat domain, and you take the target manifold to be the sphere in some Rn plus 1. So these are harmonic maps into sphere. So the very same equation translates in this equivalent way. So the fact that your minus Laplacian should be perpendicular to the tangent means that minus Laplacian should be parallel to u, which means essentially playing with the fact that u should be of the length 1 because it takes values in the sphere. Well, you realize quite quickly that minus Laplacian should be equal to this guy on the right-hand side. Okay, so let's look at this equation. So this is a nice nonlinear equation. Let's look at it in terms of regularity. So suppose that you solve this equation with some, say, in a weak form. So you're looking for H1 solutions. Then, okay, this guy on the right-hand side, so this first factor here is, say, an L1 function. U is L infinity because it takes values in the sphere. At the end of the day, what you realize that you are actually solving an equation in which the right-hand side is L1. So you immediately realize that, I mean, regularity, it's a difficult task, and that doesn't come for free using, say, soft methods. And indeed, the regularity has been, quite an issue. And for these maps, and more generally, when N is a manifold, you have regularity. So solutions, harmonic maps are regular when the space dimension M is equal to 2. And on the other hand, you just have partial regularity. So you admit solutions which might have discontinuities in higher dimensions. Well, these maps, I mean, are ubiquitous in geometry. For instance, the Gauss map, so the map that gives you, given a manifold, an oriented manifold that gives the normal as the point, is an harmonic map when the manifold M has constant mean curvature. So, I mean, these objects are quite studied in geometry as well. Okay, so let us go to some real-world applications of these maps. So, and these, in a sense, motivate the study, the fact that I started to study this kind of problems, because I was looking at liquid crystal models, and when you look at liquid crystal model, for instance, you study nematic liquid crystal, then you immediately realize that if you look at say most simple energy, reducing all the physical complexities, when you end up with an energy which has exactly this form, and in this context, U is a vector which takes values in S2. So, for instance, suppose that omega is a domain in R3 occupied by your liquid crystal. So the situation is more or less as follows. You have your domain in R3. Well, okay, you fix a point X, you zoom at the point of X, and you compute the mean orientation of the molecules of your crystal around the point X. And what you end up with a vector, which I call U, which describes the mean orientation. Say this vector is a function, so it's a map from your domain. So imagine that here you have your vectors, 2s2. And I mean, reducing all the physical complexity, the simplest energy is exactly the harmonic map energy. And this energy, despite its simplicity, is still able to capture, I mean, many physical say features of liquid crystals. For instance, the emergence of singularities, which are usually called defects in this context. Okay, this is one application. The other one application is this one. So Ginzburg-Landau. If you start with this energy, here you have a small penalization epsilon, which penalizes exactly the length of the vector U, and you say you want at some point to send epsilon to 0. Well, what emerges in the limit is exactly this map here. Okay, so these are two examples. Let us play a little bit with the boundary condition now. Suppose that for the moment I'm not imposing any kind of boundary condition, but suppose that now you want to solve a Dirichlet problem. So you fix a boundary datum on the boundary of your domain or your manifold, and you want to find an harmonic map with the prescribed boundary condition. Right. So if and this is a big if this space or this set is non-empty, here means exactly maps with H1 regularity which take the value G on the boundary. Well, if this space is non-empty, then I mean it's quite easy to get an harmonic map by minimizing the energy. So the energy at the end of the day is lower semi-continuous and coercive, and this set is closed for the weak topology of H1. The reason is that you are imposing, say, that the map V takes values in N, which is, I mean, a pointwise constraint, and so it goes in the limit using the weak topology of H1. Okay, so there is this big if here, because of course you may enter in the situation in which this set is empty, and there is a big warning which comes, for instance, in 2 dimensions. So if now, for instance, M is just the ball in R2, you take values in S1, you fix this boundary condition, which is simply the identity. Well, it's you realize at some point that this space is empty. So what to do when this space is empty? Well, there is this Ginzburg-Landau approximation that tells you something, and it's the content of the famous book by Betuel, Perzis, and Melange. And this is, say, a nice feature of these studies, the fact that when you have boundary conditions, somehow the topology, and here topology means topology of the boundary condition, because everything is related to the degree of the boundary condition, the topology drives the formation of singularities. And this analysis has been pushed quite recently by Radio Ignat and Bob Gerard to to the case of vector fields. So you are now taking a closed manifold with some Euler characteristic. Here the topology is described by the Euler characteristic, and you want to understand, I mean, what happens for vector fields. So this is the content of this paper, and essentially they are able, with a lot of technical difficulties and new ideas, to reconstruct the theory of Betwell-Berthis and Elan for vector fields now on surfaces. Okay, so this is for boundary condition. Of course, when you play with liquid crystals, most of the time you have boundary conditions. So what happens, for instance, for this case, so omega, a subset in R3, and now you take values in S2. Well, there is a famous map which is called in the community of liquid crystals EJOG, which is this map X over mod X, which now is defined in a ball of R3, takes values in S2. Well, the fact is that this map is shown to be minimizing the energy. So this map is a minimizer of the energy. And this is a nice example because, among the others, shows that minimizers may not be smooth. So you have a singularity exactly in the origin. So this is, I mean, an example for the occurrence of partial regularity in higher dimensions. Okay, so this is for the static situation. And let me go, okay, again, another example of static situation in which I change the boundary condition now. So now let's take a submanifold of the target manifold N. And let's look at critical point of the very same energy, in which now you prescribe, well, actually, you impose that the boundary of your manifold M is mapped to the submanifold sigma. So the energy is the same. If you now, I mean, minimize with this new constraint, what you get is that your map U, so your harmonic map now, verifies the very same equation as before. So you still have your, say, nonlinear equation inside M. Then you have this strange boundary condition here. And then you have a Neumann boundary condition. That means a nonlinear Neumann boundary condition that tells you that the Neumann derivative is orthogonal to the tangent at U at the manifold sigma. So these maps have a name. And these maps are called harmonic map with free boundary, not to be confused. I mean, here the word free boundary is not to be confused with the free boundary which occurs in Stefan problems and the usual free boundary problems, and simply refer to the fact that you see here your manifold on the boundary of M is free to take any values in the submanifold sigma. So this free boundary comes exactly for the freedom that the boundary that the map have to take values in sigma. Okay, these have been studied since a while, from Hamilton at the mid-70s, and then there are various results concerning existence and regularity. Okay, so this is say another boundary condition. Let's now move to evolution. Oh, sorry, no, not yet to evolution. Let's rephrase this nonlinear equation in terms of this new object regarding non-locality. So let's look at some non-local parallelism. So take M to be the upper space Rm plus 1 positive. Take sigma to be the sphere in Rn, which is now N. So your target manifold is the whole Euclidean space, and you prescribe, say, that on the boundary you take values in the sphere. Well, you realize that the harmonic map with free boundary equation actually is the Caffarelli-Silvestre harmonic extension of the half harmonic map with values in the sphere. So the alpha harmonic map with values in the sphere turns out to verify this nonlinear equation. So essentially, you have that the half Laplacian of V should be orthogonal to the tangent at V at the sphere. And if you play with this equation and use the Caffarelli-Silvestre extension, its harmonic extension exactly verify this system. So here we have this nice parallelism which has been used by used by Millot and Sire, and then I have to cite Dalio and Rivière, which studied probably for the first time these objects in the case of one dimension. Okay, let's now turn to evolution, and let's turn to evolution with a famous problem which dates in the 70s. So it's the problem which has been studied by Lis and Samson that introduced somehow the heat flow for harmonic maps. So suppose that you have, say, a map U0, and you look for a map in the homotopy class of U0, which is harmonic. So what does it mean to look for a map in the homotopy class of U0? It means that so U1 is said to be homotopic to U0 if you can deform it continuously with an homotopy. And so an idea to attack this problem, since by minimization I mean this homotopy maybe is not conserved, well, a nice idea is to study to deform through a heat flow, and then to introduce, say, the gradient flow of the energy that we saw before. The gradient flow means the L2 gradient flow, and so you end up with the study of this parabolic equation now. Okay, you prescribe the initial condition and you let your flow to start. Okay, what are the results? So there are plenty of results on this equation. The first one is exactly due to Lis and Samson, and they recognize that the condition to have a smooth flow, and so to positively solve this problem, is that the sectional curvature of the target manifold should be less or equal than 0. In this case, you have a smooth solution which converges when time goes to plus infinity to an harmonic map, which means that exactly using this flow you can deform this U0 to an harmonic map. Okay. Then there are other results which remove this curvature condition. And if you remove this curvature condition, say, for instance, you take a sphere as a target manifold, then you end up with maps which are non-smooth. So you have non-smooth situations, and what you get are maybe global results in time for weak solution, and maybe some partial irregularity result. And then you also have singularity formation analysis, means finite time blow up, infinite time blow up, what happens during the blow up time. So you have really a huge list of results on this problem. This problem, of course, I mean, it's interesting from the pure mathematical point of view, but it's interesting also from the application point of view, since it enters exactly in the liquid crystal model when you consider a dynamic situation. So if you really consider a liquid crystal with which might flow, so not a static situation, you end up with this modeling. So you have Navier-Stokes here, which is coupled through this right-hand side with the harmonic map it flow into sphere, again with this transport term. So this is a quite complex problem, and indeed, I mean, the results are very difficult. And just to recall that the basic result, existence and partial regularity, are due to Fanghualin, Chun-Liu, and Fanghualin and Chang-Du Wang. And of course, also on this equation, there are plenty of results. Okay, so I told you before that for the static situation in 2 dimensions, you might enter into problems in finding an harmonic map if you prescribe the wrong boundary condition in terms of topology. So what happens now if you if you consider this evolution equation with a boundary condition for which this space is empty. Say, for instance, take omega to be the disk in R2 and take G to be the identity. Of course, now this equation is a semi-linear equation which has a smooth solution for any positive epsilon, and now you want to send epsilon to 0. You realize that if you don't have the evolution when you send epsilon to 0, and this is the content of the book by Betuel, Brazils, and Elant, there is a creation of vortices, maybe a finite number of vortices if you start with, say, with a good boundary, with a good initial condition. And so the topic is, can you track the evolution of the vortices of the singularities, say, in omega? Is there an equation that describes the evolution of singularities? Well, the answer is yes, and has been studied for maps by, for instance, Gerard and Solner, Fangualin, and Sanguier and Sarfati, using different methods. And with Giacomo Canevari, we studied, so we have a paper that came out this year that exactly studies this situation in the case in which U is a vector field and omega is a closed manifold. And here, so you don't have the boundary condition, you simply replace the condition on the boundary with a condition on the Euler characteristic of the manifold. Okay, so now this is for Dirichlet boundary condition. Now, let's come back to the geometric problem of free boundary. And now let us try to deform a map U0 to an harmonic map, but keeping the nonlinear boundary condition here, the free boundary condition. Okay, so if you so this problem, I mean, turns out to be essentially this evolution equation. So you have the heat flow for harmonic map, you have the boundary condition here, and you have, say, the free boundary condition, and you have the Neumann boundary condition. Okay, this is again an old problem which has been studied again by Hamilton, Chen and Lin, and then Struve, and they got the existence and partial regularity result. Okay, now we want to revisit this problem here using, say, the non-local interpretation we gave before for the static situation. Okay, so now take sigma again to be the sphere in Rn. So n, the target manifold is Rn. And take M to be the semi-space. Okay, now it turns out that if you look at this system with n to be Rn and sigma to be the sphere, well, it turns out that this equation is related to a kind of Caffarelli-Silvestre extension of this non-local PD. Now, here non-locality is in space, okay, and time. So you are taking the square root of the heat operator. What do I mean with that? So this is something that has been studied. So this kind of non-local operator has been studied by Nystrom and Sende and Stinga and Correa simultaneously. And say this operator, this square root of the heat operator, is essentially related to the Neumann derivative of U, of capital U, with now capital U is, say, the solution of the heat equation in the extended space, which on the bottom space, say, as a trace which is given to U. Okay? So this is, say, the extension definition of this operator, which I mean can be given also in another form. So you have at least two other possible definitions which are completely equivalent, either to look at the Fourier transform in space and time, or either to look at this singular integral definition. Here, this K you see it's essentially the heat kernel with, say, it's 1 over tau to some power of the times the heat kernel. So this three definition turns out to be equivalent. Either you define it through the Fourier transform or to the singular integral, either to the extension. Okay, so our purpose now is to try to understand what happens when. So we look at this equation. So n is now the whole space. Sigma is the sphere in Rn, and say if you look at as a local problem, you want to solve this equation now, this PDE. Where now, so since this equation is non-local in space and time, you impose a kind of say initial condition also for negative time. So you are given a function u0 which depends on x and might depend on t, and you impose that your solution should be equal in from -infinity to 0 to u0. Okay, so the idea now is to try to study this problem by relaxing the boundary by relaxing the constraint here. And the simplest way to relax the constraint is to introduce this Lindbergh-Landau penalization. So instead of considering the equation, say this nonlinear equation, you consider this other equation with a small epsilon, and then you want to send epsilon to 0. Okay, so some simplifications. First, we actually look for initial condition. Since we are interested at the end in a geometric problem, we look at initial conditions that do not depend on t. So this u0, which might depend on x and t, now depends for us only on x. Okay, so if you want to study this equation and you want to interpret this operator in terms of the extension, well, you end up now with this problem in the extended space. So you have the heat equation in the extended space. You have, so imagine, to put that this is Rm. This is the timeline, and this is Rm plus 1. So here, in this room, you are solving the heat equation. Here, for T positive, you are imposing the boundary condition on the Neumann derivative, and here for T negative, you are imposing this other boundary condition. Okay, and you solve for all times. So you don't really have a Cauchy problem, but rather, so you have the heat equation with these two boundary conditions on the bottom space. Okay, so what shall we do with this problem now? So it's well, one can show, for instance, that for any epsilon positive, you can construct a solution of this equation of this system, and the essential trick. So the essential tricks are two. First, you can reduce this problem to a real Cauchy problem, since this u0 does not depend on t. So you can really solve this problem like a Cauchy problem by using the Caffarelli extension for negative times, just in space. Then you prove existence of a solution, essentially relying on the fact that this equation combined with this boundary condition is a gradient flow equation for the energy that you expect. Say you have Dirichlet energy plus, say, a Ginzburg-Landau penalization that now acts only on the boundary condition. Okay, so existence of a smooth solution for any fixed positive epsilon, I mean, it's something that you can do. But then you want to pass the limit. And here, you may have some troubles, because you see, you have this highly nonlinear well, here you have this highly singular, say, nonlinear boundary condition, and so you may have problems in going to the limit. What to do now? Well, you use a method which is usually called Chen's trick, which essentially uses the fact that you are playing with the sphere, and so you're using the symmetry of the sphere in this way. So first of all, you realize that if you suppose that here you are taking value in R3, so this cross product is very well defined. Otherwise, you have to use the wedge product. So it's a little bit more technical, but can be done. So first of all, you realize that if you take this cross product, then this cross product is actually a divergence. So it's the divergence of this object. Okay, now what to do with this divergence? This divergence now, it's since this is a divergence of something, this is easy to go in the limit, because you can play with test function and put this divergence on a gradient of a test function. So this object, which is somehow quite complex in the limit, turns out to be easily treated by using this reformulation. The point now is that the boundary condition, you see, you're saying that the Neumann derivative is parallel to U epsilon, which means that if you test with the cross product of U epsilon, this guy disappears. So essentially here you're using this reformulation plus the fact that, say, with the energy regularity that you get, you easily go in the limit inside, so in the heat equation. And at the end of the day, you are able to reobtain that the Neumann derivative is exactly orthogonal to the tangent at the sphere. Okay, it's a trick that it's quite common in the Ginzburg-Landau community, and to treat exactly harmonic maps into sphere. Okay, so once you have proven this is a global result. So you have an existence of a solution U which has energy regularity, say H1 in space, essentially. Now you want to prove some higher regularity, maybe partial regularity result. Okay, so which is the strategy that one usually put in practice in this field? So the very first step is to identify some monotonic energy. You need some monotonicity formula for some energy, usually some renormalized energy, maybe the real energy multiplied by some other function. Once you have identified this monotonic energy, the second step is to prove some epsilon regularity or clearing out result that essentially mean that in small ball, so if the energy is small in a ball, then maybe in a smaller ball you are smooth. After that, you play with a covering argument that gives you that in the limit you obtain that your solution U is smooth outside a set in the space and time, which has some parabolic Hausdorff measure finite of some finite dimensional parabolic Hausdorff measure. And of course you want to understand of which dimension. Okay, this is just the program. The first program, of course, is to identify the energy that is moved. Well, essentially playing with the fact that here you are using the caloric extension, so you are extending with the heat equation. Well, it's quite, maybe not easy, but quite natural to try with this energy. So you take the energy here, you see, it's the Dirichlet energy, times the gradient in x and y of U epsilon, and you multiply by this factor, which I now tell you what is it, and you integrate in this parabolic cylinder, and then you also control on the boundary the Ginzburg-Landau term. Now, what is this G? Well, G is the backward heat kernel. Okay, so it turns out that this is a matter of computation. So you start taking derivatives with respect to R, that this function is monotone, non-decreasing with respect to R. Okay, so this is the first ingredient. The second ingredient is the clearing out. Clearing out means that you can find a threshold below which, so if the renormalized energy is below this threshold, then your U epsilon in absolute value is greater than 1/2. So it's close to 1. Recall that you really want U epsilon to be close to 1, because if the closer it is to 1, the less effective is the Ginzburg-Landau penalization. Okay, and you are closer, and you are close to 1. I mean, you are bigger than 1/2 exactly in this parabolic ball. Okay, not only clearing out, you want epsilon regularity, which means now that if you can identify a threshold such that if the energy is below this threshold, then your solution in a small ball is C1 plus alpha. And the point is that this constant that appears here depends only on the threshold eta naught, of course on alpha, but is independent on epsilon. Okay, so this is essentially, these are the two ingredients, the basic ingredients. And what is the outcome of what is the result? Okay, as I told you, you can construct a global solution of the flow. Well, this solution is smooth outside a subset sigma of the space and time. So Rm is the space here. Sigma is locally finite m-dimensional parabolic Hausdorff measure. Parabolic Hausdorff measure means Hausdorff measure evaluated in terms of the parabolic distance. Okay, not only you can find time such that the intersection between this singular set and say Rm times this interval of time. So for times greater than T naught, your solution is smooth. And not only smoothly, you can quantify the smoothness, and you have an L infinity bound on the gradient. And not only you have a decay on the gradient. That means that when T goes to plus infinity, your UT converges to a point on the sphere. And you can also, control the dimension of the slices of the singular set. So for any T, of course, less than T0, this sigma T has a finite m-1 Hausdorff dimension. Okay, so this is the theorem. Let me say also that since we have been so there have been a lot of talks dealing with blow-ups. So this, if you take m equal to 1, so you are looking for the one-dimensional flow, which means that it's R2 here in the extended variables. Well, for m equal to 1, this flow, there are initial conditions for which this flow can develop a finite time blow-up. And this is the content of this very recent paper by Yannick, Yunchen Wei, and Zheng on the American Journal of Mathematics. Okay, so this is regarding this flow. I guess. Okay, let me conclude with the possible other flow. Here, if you think back to the harmonic map equation and then to the heat flow of harmonic maps, so the harmonic map equation, say, into sphere was this one, so minus Laplacian of u orthogonal to the tangent at u of the sphere. Then you want to study the heat flow of this equation and you put the time derivative. Okay, now, if you want to go fractional, you take 1/2 of the Laplacian, you impose the very same orthogonality condition. You want to study a heat flow, and why? why you have to study this very complicated non-local in time and space flow? Why not to study this flow here? I mean, this is probably much more natural at first to be studied. So you just take the L2 gradient flow of the energy related to this equation. Well, the point is that this flow has been studied quite a lot. It has, there are beautiful results. Some of them are this one, for instance, in this last paper by Yannick, the same group as before, they studied the blow up, which now occurs in infinite time for this equation. Well, maybe you want to see whether you can reproduce the very same results we have for this flow. So if you look back at the program, say first monotonic energy, well, you realize that for the moment, we don't have any monotonicity formula for this flow. So if you want to start this partial regularity result, the very first ingredient is this monotonicity formula, which is for the moment absent for this flow. So this is, if you want, an open problem to try to see whether you have a monotonicity formula in the spirit of the one that I showed you before, maybe another one for this 1/2 flow. Okay, so I think I can stop here, and thank you very much for your attention.
So now it's time for question and comments. Are there any questions? Yes, please.
I have two questions.
Yes.
I'm a little bit confusing that because your operator is not only the space, but also the time is a non-local. So
Yes.
how to define the notion of the local in time solution? Because in your slide, you use a Fourier transform with respect to the time and the space, so that you can construct a suitable kernel.
Yes.
So how to define?
No, okay. Thank you for your question. So it's okay. These let me go. So these three formulations say Fourier, singular integral, or extension are equivalent if you're not considering, say, initial condition essentially. Here we are relying on the fact that this operator is exactly the Neumann derivative now on not on Rm times R, but on Rm times 0 plus infinity. So because we are imposing the equation here. So I'm not claiming that my problem is completely equivalent to these formulations when I take the initial conditions.
In order to construct a global in time solution, maybe you assume that the solution exists global in time. If you expect the global in time, so that you use this formulation, because at the
global means also minus infinity.
No, plus. Because at the negative time, you define that factor u equal to the initial data, right?
Yes, essentially, yes.
So the part for the time is basically we don't know the solution exists global or local. So that how to use this code?
Well, okay, you know that it's global if you look at this problem. And then the problem is what happens when epsilon goes to 0. And you show that it's and it's global in a weak sense also when epsilon is 0. But for this equation, I mean, okay, for various reasons, you can prove that okay, this equation is reformulated in terms of this extended equation, and this extended equation has a solution in a proper weak sense, which is globally defined in time.
I see. Sorry, I confused. The second question is that what happens if you change this fraction order, the different order?
Okay, thank you very much. So at the level of existence, nothing changes. So we can prove existence also, well, nothing changes in terms of result. Of course, the equation looks different. And here you have weights which depend on the extended variables y. And here you have, say, an elliptic operator with weights, but which is, I mean, a good elliptic operator. So at the end of the day, even for S different from 1/2, you get existence. And I mean, the regularity result, yes, can be done. It's a bit less transparent than the case 1/2, but it can be done. And also it can be done if you change here. Here I did everything in the case in which the target manifold is the sphere, but you can essentially replace the sphere with a closed with a compact manifold. So it's I mean, can be generalized to the more general situation. Yes.
I have a small comment. Many people try to consider fractional equation for the simple case, and they apply for the Sylvester-Cafali intention. And can you do for general Laplace operator, fractional Laplace operator, where you cannot apply Sylvester-Cafali intention?
No, no.
So what happens when you consider for the general fractional Laplace operator? Yeah. And simplify, you cannot use Sylvester-Cafali intention.
So you mean so what happens if you consider a general non-local operator?
Yeah.
Well, I don't know. Honestly, I don't know.
Because, for example, you can design a monotone formula for the general fractional operator. That is possible. That is possible. Yeah.
Yes, no, I thank you for your question, but I didn't. Well, okay. I would say that if you can show me a monotonicity formula, maybe you have something to start with. But this is just an educated guess. I don't know. Any other question?
So my question is some continuation of Kawakami-san's question. So you study the half of heat operator, and you said that if you consider other exponent, so you can also prove something. So how about the weighted monotonicity formula? Monotonicity formula for weighted energy for other exponent.
Yes. So
sorry.
yes, it's well. The structure it's essentially the same. The difference lies in the fact that so there are differences in the heat kernel now here, which is of course not the heat kernel of the heat equation. So it's the heat kernel of, say, it's the fundamental solution of the equation that you get by extension. And then you have some weight here, which depend on the y variable, so the one that comes out, so the extension variable, say.
So that kind of weighted energy works well.
Yes.
Thank you.
Thank you.
Okay, so maybe still there are many questions, but let's move on to the second. So let's.
And this is, I will, or maybe later, right?
Okay, so now let's move on to the last speaker for today. And also this was the conference. The last speaker is Professor Tatsuya Miura, and he will talk about the classification and the stability theory of planar P elastic. So please.
Thank you very much for the introduction, and also thank for the organizers for this kind invitation to be here. And also I'm very honored to be this accidental last speaker of this conference. Okay, and also I'm sorry that I actually got the sore throat, so let me use my microphone, and I need to whisper talk to you. But anyway, in this talk, I will talk about the classification and the stability theory of planar P elastic. And this is joint work with Kensuke Yoshizawa at the Kyushu University. Okay, and in this first slide, I actually summarize all the important points of this talk. And the main point is that recently we have found interesting to us the stabilization phenomenon in the P-elastic theory, which I want to talk about now. So I will talk about P-elastic theory, which is a variational problem concerning the P-bending energy, which is nothing but LP curvature energy defined here. So we consider planar curve. Planar curve is denoted by gamma. And we consider the energy BP gamma, which is defined by just the LP norm of the curvature of the curve. And if you use the occurrence parameterization for curve, then the energy is nothing but the LP norm of the second derivative of the curve. Okay, so this is a very simple and important energy, geometric energy. And in fact, the classical case is equal to 2 just corresponds to the theory of Euler's elastica. So this is classically called bending energy or elastic energy. And actually, this is studied from 18th century. It's a very old concept. But recently, we found that we studied a generalization of this problem with respect to this exponent P. And recently, we found that in the degenerate regime, meaning that P is strictly greater than 2, then we discovered a variational stabilization phenomenon. And this is our actually main theorem, a summary of our main theorems. Okay, this is a statement. Let P is between 1 and infinity. And we prepare large P0 and large P1, which are 2 points in plane. So we consider 2 points here. And we consider a planar curve like this in the plane, whose endpoints are just given by P0 and P1. Okay, and this curve has length large L. So clearly, this L needs to be larger than the distance of P0 and P1. Okay, and we consider the set, the admissible set. We denote it by A pin, meaning it is the set of occurrence parameterized W2P soft curves in the plane with length L. And the endpoints are pinned at the endpoints P0 and P1. So just the positions are fixed, and the direction, tangent directions are allowed to rotate. So actually, due to this boundary condition, the curve can rotate. So actually, this boundary condition is quite under this boundary condition. The critical points can be easily become unstable instance. And actually, it was already known that if P is equal to 2, there are only the only local minimizers are given by global minimizers. And in fact, recently we extended this fact to some of the general exponent. And this is the first result. If P is less than or equal to 2, including the classical case, or if P is larger than 2 and satisfying some condition on the boundary condition, meaning that the endpoints are sufficiently close to each other, then there exists no local minimizers of the P bending energy in the admissible set AP, other than unique global minimizers. And here, unique means up to invariance, because, for example, reflection is also has the same energy. So it's actually the quite strong uniqueness result on stable solutions. However, very recently, we have found that there are very new stabilization phenomenon in the degenerate regime. And more precisely, we can show that if P is greater than 2, and also the boundary conditions satisfy some this relation, meaning that boundary points are far from each other, then there emerge, in fact, uncountably many local minimizers of this energy. And also, we can extract some subsequence which diverge, whose energy diverges. So in this sense, we should say that in the degenerate regime, we have a very strong and non-trivial variational stabilization phenomenon. Okay. And the purpose of rest of this talk is to explain why this kind of stabilization phenomenon occurs. Okay. Okay, let me go into the details. So the table of contents, we first introduced the P-elastica theory more precisely, and then we go into our results. First, we give a classification and go into boundary value problems. And finally, we talk about the stability theory. And this is based on the series of joint works with Kirsty. Okay. What is Euler's elastica? Actually, this is a very classical concept, and actually the most basic 1D mathematical model for pin bending structures. And and this model actually also appears in many contexts other than bending structures, actually pendulum, rock, balloon, architectures, and image processing, and so on. There are many applications. But anyway, first, this problem is proposed by Daniel Bernoulli. And soon later, Euler, in a sense, solved this problem on the level of the critical points. And actually, he has already classified in a beautiful way. And this is actually his figure, Euler's figure. And this actually corresponds well to real phenomena. And this is due to Max Born, who is famous in quantum mechanics. But actually, his dissertation is about this elastic problem. And this is coming from his dissertation. Then this is actually the first study to compare the elastic theory and real phenomena in an accurate way. Okay. And for the classic elastic problem is a variational problem for bending energy, which is defined by the L2 norm of the curvature for planar curve, S denotes arc length, and K denotes the sine curvature. Okay. And this is proposed by Bernoulli. And if we say that the curve is elastica, it is a critical point of the bending energy under the fixed length constraint. So this fixed length constraint is quite important in this context. So if we consider this kind of constraint, then by using the standard multiplier method, we can say that if a curve is a critical point, then there exists some multiplier lambda such that this is the this the first variation of the energy B plus lambda L vanishes at gamma. So this is the actual definition of the elastic. And by using this condition, we can derive the standard in a standard way the Euler-Lagrange equation, which is actually given by just the second order ODE for the curvature, which can be solved by Jacobian elliptic function explicitly. So any critical point is actually any elastica is regular, and also K can be expressed by Jacobian elliptic functions. So we have well classification, and also we have explicit formulate even for the curve itself in the Cartesian coordinates. Okay, and this is well known. However, if we consider the p-bending energy, the situation becomes a little bit more involved. And so p-bending energy is the LP counterpart of the bending energy. And actually, this energy has also been widely studied because this is simple. And for example, to my understanding, mathematically, this energy has first appeared in the context of image processing by Masno and Moore, also Ambrosio Masno, and so on. And later, this is studied in many ways. For example, in terms of critical points, or there has some ambient approaches has been developed, seeing that the curve is the boundary of some given set. And also, there are some studies on gradient flows of this p-bending energy. Also, Professor Okabe here is pioneering works on this p-elastic flows. And also, there are many other studies. But in fact, there were no classification results for p-bending, p-elastica. So our first purpose was to develop p-elastica theory by establishing classification result. And actually, this was done in a good way. So let me first define p-elastica. This is a straightforward analog of the classical elastica, which is defined by for some multiplier, this derivative vanishes at the curve gamma. And we can derive the Euler-Lagrange equation at least in a weak way. But then you find that here you have a nonlinear diffusion term, although this is one-dimensional. But now I would like to point out that some kind of interesting fact that here, in terms of curvature, you have a porous medium type nonlinear diffusion. But from the same problem, we can also derive a different form of the equation, which involving p Laplacian type nonlinear diffusion. I'm not sure why this occurs, but anyway, for me, this looks a little bit interesting. Okay. But anyway, we have nonlinear diffusion term here. Okay. So due to this nonlinear diffusion, of course, regularity is not so straightforward as the classical case. And also, the more difficult point is the classification and explicit formula. Actually, we cannot use Jacobian elliptic functions or actually previously known p-elliptic functions devised for studying some kind of a Laplacian type equations, for example, by Professor Takeuchi or something. Anyhow, however, we could classify the planar elasticity. So first of all, we have obtained optimal regularity, but I do not mention the optimal regularity, but I just say that any planar P elastica is actually at least has regularity W31, which in particular ensures that the curvature is always continuous at least. And actually the optimal regularity depends on P. And more importantly, we have obtained a kind of explicit formulae, a series of explicit formulae for planar P elastica. So, and the point is that, one point is that we have a threshold. Actually, non-degenerate case and degenerate case has a different kind of curves. And first of all, in the non-degenerate regime, meaning that P is less than or equal to 2, then after similarity and representation, any planar P elastica is given by a part of these curves. And I just give you some explicit formula for those curves. But anyway, we have two almost trivial cases. One is linear elastica, which is segment, and the one is a circular elastica, which is just a circle. And intermediate cases are a little bit special curves for this problem. But anyway, we have 5 cases, and in the degenerate regime, meaning p is greater than 2, then the case 3 turns out to be a little bit complicated case, which is called flat core P elastica. Maybe Professor Bello is very familiar with this concept, but anyway, so I will show you more precisely later. Okay, so first of all, I show you the precise formula for case 2, 3, 4. And to describe those cases, we have introduced new types of p-elliptic functions and used non-p-elliptic integrals. Those are used by Watanabe. Actually, those are special parts of Takeuchi's more general generalization of p-elliptic integrals. But anyway, we can obtain this kind of explicit formula because actually I haven't defined p-elliptic functions, so you cannot see the precise definitions. But the point is that for all of the curve, the curvature can be represented by directly the p-elliptic functions. And actually those functions have at least qualitatively quite similar properties to the classical Jacobian elliptic equations. So by using this fact, we can actually extend very many of known analysis to this p-elastic case. Okay, and now I show you some figures of p-elastic A. In the case 2, we have a sign changing curvature. So we have a kind of inflectional curves, which we call a wave-like p-elastic A, because in the classical case, those are called p-elastica. And actually, Jacobian elliptic function have modulus, which is one parameter. So it's a kind of one parameter family of curves. And by changing the modulus, the shape of the curves changes, as in those figures. And taking the modulus to be 1, then we reach the limiting case, which is called borderline elastica. And this is the only case where the curve has no periodicity. And every other case is the curve has periodicity. Okay. And the last case 4 is called orbit-like elastic, p-elastic. And in this case, the curvature doesn't change its sign. Okay. Anyway, we have this kind of shapes, and we have just obtained all of the possible cases with explicit formula at some level. Okay. And this is the case where p is less than or equal to 2. And if p is greater than 2, we have another type of elastic, which is called flat core p-elastica in this context. And actually, so these are a way to define the curves, but anyway, these are not so important in this talk. The most important point is that we have this kind of non-periodic curve with flat path, as in many other problems of nonlinear diffusion with degenerate diffusion. Okay. And actually, we have some freedom. For example, if we just shift this loop into this way, then all of those curves are still critical points of this problem. Okay. So this gives a new phenomenon, but actually this has been already known by Watanabe. And also maybe you can easily imagine by using the other context in a sense. So, but anyway, this is a new type of curve here. Okay. So then we have classified all the possible critical points. Then with this classification at hand, we can go into boundary value problems. And actually, for certain boundary value problems, we can even classify all the possible solutions to that boundary value problem. But one point I want to emphasize is that even in the classical case, if you choose a very difficult boundary condition, then it is still difficult to classify the possible other critical points, even though we have explicit formula. because we have Jacobian elliptic functions and integrals, and so value problems involve a very complicated system of transcendental equations, which is quite difficult to solve. So in this way, in this sense, for difficult boundary value problem, it is difficult to solve it. But if we consider our current problem, which we call pinned boundary condition, then we can actually classify all the possible cases. Okay, let us recall that our pinned boundary condition is given by in this way, as in the blackboard. So we have the length L curve with endpoints pinned at P0 and P1. And then in this problem, we can say that any critical point is given by as in these figures. And one possibility is we call n arc. And so I don't give a definition, but this is as here. So this is one arc, and any n arcs are certain periodic extension and rescaling of the original one arc. So this is one arc, and this is two arc, and this is three arc. And a similar thing occurs for loop case. And also, so we have arc type critical points, and also at the same time, we also have loop type critical points. And actually, we have two cases, depending on whether the exponent is degenerate, or also depending on the distance of the endpoints. If in the non-degenerate regime, or even if degenerate, but the endpoints are close to each other, then we have this kind of periodic loop type solutions. And this is one loop, and this is two loop, this is three loop, and so on. We have countably many candidates. But if in the degenerate regime, and also the endpoints are far from each other, then we can have some kind of flat path critical points. And this case is a little bit different, quite different from this case, because the critical points may have no periodicity in a sense. And also we have kind of freedom with respect to the position of the loop. Okay, so this is kind of difficulty in this context. But anyway, we can still classify all the possible critical points. And also, additionally, we can say that any global minimizer among those critical points, any global minimizer is just given by this simple one arc by just computing all the possible energies of those critical points. And actually, in fact, we first proved an abstract existence result for the global minimizer, but this is actually not difficult, straightforward. Okay, and this can be done. How to prove this? So I just give one comment, an important comment, that in order to classify those critical points, we use this additional boundary condition obtained as a natural boundary condition by computing the first order derivative of the energy. And by using this condition, computing the boundary condition, we can additionally obtain the boundary condition that the curvature vanishes at the endpoints. And this actually makes the computation quite simple, because if we can a priori know this fact, every possible critical point has a very periodic structure in a sense, due to the fact that the curvature is given by p-elliptic functions, which is periodic. So just knowing this fact, we can obtain a very surprisingly good reduction to classify all the possible critical points. Okay, and this is the second mouse. Actually, this is done in our second paper, and then we entered the stability analysis of those critical points, and this is the most difficult part actually in this talk, because in the p-elastic problem, For example, first of all, even in the classical case that P is equal to 2, stability analysis are a little bit complicated in the sense of computation because our problem is higher than that. And actually, although the critical point can be explicitly computed, so the second order derivative is also explicitly computed, but in order to estimate the sign of the second order derivative, it is still difficult. It involves elliptic functions. But anyway, in some good cases, many works are done, have been done. But the point is that we are now considering P is not necessarily 2. So in this case, even conceptually, the stability analysis is delicate because now we have no Hilbert structure of this problem. So the second variation analysis doesn't not straightforwardly imply the stability in the nonlinear level, original problem. So this is the kind of difficulty. And also we have a trivial loss of regularity in this context. So this also makes the problem more involved. For example, the second variation of the P bending energy may diverge or degenerate for critical points. Maybe you can imagine this fact by showing this, by seeing this easy computation. For example, if P is less than 2, then this term may diverge in a sense. And also if P is greater than 2, this is less than 2, which yields some kind of degeneracy in the infinite dimensional analysis. So this is difficult. Okay, so second variation approach in principle doesn't work well without any ingenuity. So we have devised several new, actually very new approaches which do not rely on second variation arguments in this context. Okay, these are actually both in a sense main results of this talk, which I would like to emphasize. Okay, first of all, in the context of instability, we have developed a kind which we call cut and paste trick, and in stability we developed a kind of divide and relax method. Now, in the rest of the talk, I explain this method. So, for example, I talk about instability, and to prove instability, now we prepare a given critical points. And we want to prove the instability of this one. And instability means non-local minimality. So in the neighborhood, we want to directly construct the curve which has less energy in a sense. But this is actually quite difficult, mainly due to the fact that we need to preserve the length of the curve because our admissible length fix the length. And so this fact actually quite obstructs the perturbation in a geometric way. So the problem is in a sense not trivial. So actually it is difficult to construct an energy decreasing perturbation while fixing length. And the trick we have, our trick is a kind of a very simple indirect argument for this problem. So actually we construct a perturbation of fixed energy and length. So both energy and length are fixed, but which has the curve has not enough regularity. In the sense that it cannot be a critical point of the curve. And why this works? Because if we assume that the given curve is a local minimizer, and if we construct this kind of fixed energy and length perturbation, then the perturbation itself is also a local minimizer. Because in the neighborhood, if it has the same energy as the local minimizer, then of course it is a local minimizer. So it must have the same regularity as the critical points. But if it has no such a regularity, then we can obtain a contradiction. So in this way, the proof works. So for example, if you have this kind of wave-like elastica, and if you have this kind of 3 inflection points, and just we prepare a well-prepared 3 points, and if we just rotate this part and construct a perturbation just by using cut and paste, then of course this has the same length and the same kinetic energy, but you can easily notice that at this point the curvature is discontinuous. And as I showed you, every critical point must have a continuous curvature. So this is a contradiction. And in this way, we can prove that this kind of curve is unstable. So this is the main idea for instability. And actually, this actually looks like a little bit ad hoc argument, but actually this idea works well for a quite general functional of not necessarily p-elastic, p-bending energy. And also, actually, this gives us simpler proof of instability, even for Euler's elastic with p is equal to 2. But anyway, okay. So this is the instability result. And also by constructing many kinds of cut and paste perturbation in this way, then we can say that in the pin boundary problem context, we can say that most of the critical points are actually unstable, not local minimizers. So for example, n arcs are unstable if for all n is greater than or equal to 2. And also all loops are unstable. So by using this fact, we can already say that in the first case, the only stable solutions are one arc. This is uniquely uniquely determined up to invariances. And also, so this is the this is one result, and this method actually partly works for loops with flat path. And actually, this flat path case is a little bit difficult in view of stability. But anyway, a part of those curves are also unstable by using this method. For example, if one loop touch at the end point, then it is unstable. And also, if there are two loops with opposite sign and touching to each other, then this critical point is against unstable in this problem. And we can say that this kind of thing. So now, at this moment, we can say that any stable pin P elastica is necessarily either a global minimizer or a kind of n loop with flat path. And for example, this one is unstable. This one is unstable due to these opposite loops, but we still have possibilities. For example, this one has between each two loops, we have non-degenerate segment. This is one point, and also at the endpoints, we have non-degenerate segment. And the last case, we have degenerate segment, but there the loops have the same directions. And those cases are still difficult, not shown to be unstable. And actually, it was quite open that if there exists actually a new local minimizer in this program, but recently we have found that in the third case, we always have stability. Okay, this is the last result. So in our the most newest paper, which we have shown that every alternating n loop flat path is stable in AP. So here alternating means that it has segment, loop, and segment, loop alternately. And in this case, we could show the stability. And this is actually a completely new example of the local minimizer in this p-elastica problem. Okay. And the proof, so finally, I just sketch the proof. And first, we just divide the given alternating n loop with flat path at the endpoints and the top of the loop and in the middle of the segment and so on. And we just divide this curve, and we prove that even after a perturbation, this kind of single Hawk has a special minimizing property to show that even in the original program, we can say that for every curve in a small neighborhood of this curve, the curve has less than greater than or equal to this curve. Okay. Yes, so this is the kind of divide and relapse method. And actually, one point is that we first divide and relax the class of the competitors, even to include discontinuous competitors. And by using this kind of relaxation method, we can obtain an additional free boundary condition, which again makes the reduce the possible candidates, and then we can actually compute the minimal energy explicitly in this problem. Okay. And now you may see that this is also looks also ad hoc, but actually, so this is actually ad hoc argument, but actually in a wide context, similar idea, we have used similar ideas in different problems. For example, with Professor Okabe here, we have obtained some kind of generalized isoparometric inequality, and there actually I have also used divide and relax method in a certain sense. And also in a different paper of myself to prove a real type inequality for curves, then I have actually used a similar kind of divide and relax procedure. Of course, the problem is quite different, but the rough idea is actually same. So I think at least for one-dimensional problems, this kind of method works even for other contexts. Yes, okay, so maybe I should finish. Okay, finally, I just give some comment. And so in this problem, actually we have proved a kind of stability in the interior case in some sense. So for example, actually this kind of flat core solution has obtained in a kind of reaction diffusion problem involving P Laplacian. And there we have also this kind of solution with freedom of on the position of the transition layers. And if we parameterize the length of the segments here, then we of course have some kind of simplex type constraint. So we can say that the set of this kind of solution form a simplex. And this is indicated by Gueda and Bellon in a classical paper. And the stability of those critical points, and the stability means dynamical stability, corresponding for the corresponding parametric equation. The stability is studied by Takeuchi Yamada and Takeuchi and so on. And in particular, Takeuchi and Yamada proved in the boundary case, this kind of critical point is always unstable, dynamically unstable. So from this, in a small neighborhood of this solution, we can find some initial data with not converging to this case. However, in the interior case, the stability is, to my understanding, this is not solved, but Takeuchi obtained some kind of partial stability result in the interior case by restricting the neighborhood of the given critical point. But anyway, full stability is completely open to my understanding. But in this variational stability context, actually we could prove all the stability in the interior case because our alternating critical point roughly corresponds to the interior case. So in this sense, this would be give some interesting insight to in a wide context of nonlinear diffusion, I believe, but I'm not sure. I'm very happy to have your comments on this point. Okay, and this is the last slide. I have classified all the critical Prager elastic at the level of critical points, and solved the pin boundary value problems, find unique global minimizers, and turned into the stability analysis. And actually, generic critical points. For generic critical points, we have classified the stability. And in fact, we have discovered a new stabilization phenomenon in this degenerate regime. And there are some open problems. The trivial open problem is the remaining classical alternating case. In this case, we don't know this is stable or unstable. Actually, this is completely open. And also, for example, we can consider a corresponding dynamical stability, because dynamical stability means that we consider some kind of corresponding p-elastic flows, parabolic equations to this problem, and consider the dynamical stability. This is not known. So once we know our variational instability, then of course this is also unstable in the p-elastic flow. But even if we could show the variational stability of this problem, we don't know the dynamical stability. So actually, this is a kind of open problem, which I would like to address later, maybe. But anyway, we have still we don't have dynamical stability on this context. And also there are, of course, we can study other boundary conditions and also spatial curves, or perhaps surfaces, even more surfaces, which are very difficult, I think. But anyway, there are still many open problems in this problem, I think. Okay, that's the end of my talk. Thank you very much for your time.
Is there any question or comments?
Some slide you mentioned about the instability.
Yes.
So you said that you can generalize it to the more general function f.
Yes.
So I wonder, do you need to assume some condition on f? I mean, not such as a monotonicity or convexity.
Yes, indeed. So the only yes, so of course not very general class, but our general assumption is that every critical point is of class C2. So it's a kind of abstract condition. But for example, if P is smooth, for example, outside zero, and at the zero, you still have some kind of condition on the non-degeneracy of the second order derivative, then you can obtain easily the C2 or maybe smooth regularity of the critical points. So I think our assumption is to do not need to assume monotonicity, perhaps, but some kind of regularity and the structure at the origin of them, I think. But anyway, what we have indeed assumed is every critical point is of class C2.
Any other question?
You said that in stability theory, it is really important to the length constraint.
Yes.
If you consider the length penalization problem, then stability or instability study will be more difficult. Or
Yes, stability is actually difficult. Of course, our instability result directly works for length penalized case if the penalization is positive. But in terms concerning stability, it is still difficult. And actually, even for P is equal to 2, there are no many stability. To my understanding, no stability, general stability analysis has been done. So length penalization problem has a quite different, because most of stability analysis which has been done previously uses arc length parameterization. So actually use the fact that all the competitors have the same length. So yeah, actually in the length penalized case, we need an additional freedom. So actually previous method doesn't work straightforwardly at least.
Thank you.
Yeah.
So may I ask a question?
Yes.
So in this case, in this result, you can explicitly write down the minimizer.
Yes.
So in this case, maybe you can consider the limit of the minimizer as p tends to 1 or plus infinity.
Yes.
And so in this case, if you could prove the gamma convergence of the p elastic energy as p tends to plus 1 or infinity, you can also extend this result to the limiting case. If the minimizer converges to some limit
For boundary value problems, for example.
yes.
For yes, maybe there's no need to use gamma convergence, but we can just actually directly compute the behavior of the minimizer explicitly as p goes to infinity. And actually, if p goes to infinity, it goes to the circle, circular arc. And if p tends to 1, it forms corner maybe. This is a really interesting and non-trivial problem.
Maybe the regularity.
If p goes to infinity, it's clear that the minimizer is a circular arc. Okay, but yeah, if p goes to infinity, p goes to 1, then a little bit complicated. But maybe still, I think our formula can be used to obtain the unique, for example, minimizer in this context, or limit. We can detect the limit. Actually, there are many minimizers, because in the case that p is equal to 1, it is a total absolute curvature, which is, for example, if you have a convex curve with a different tangential direction, then the energy is always same. So the case that p is equal to 1 is a kind of special, but then still we can say something interesting by taking the limit. Yes.
So any other questions or comments? Not the case, so let's thank the speaker. Okay, so this is the end of the program today. And so now I'm still here, so let me